All right, today I'm going to talk about question 310. So the idea is to find the minimum height trees. There's a couple ways to do this. First, we can obviously build, first of all, either way, we need to build a tree using some kind of data structure. Instead of the edges, we can have a node and it's connected childs in a data structure. And it can be a linked list, it can be a map or whatever. And then I can do DFS to or BFS to find the depths of the tree for each node, and always keeping track of the smallest node, smallest height, and then just return. And for the time complexity, that will be an n squared operation because for doing it to find the height of a tree, that's an ON operation, and we need to do that for each node. So that will be n times n, which is n squared. And another way is we can do something called a topological sort, where we start from the leaf nodes and we try to um, remove it and remove all the leaf nodes and also um, uh, keep track of any additional leaves that we can create by removing a node. And we can keep doing that and keep trimming off leaf nodes from the tree and all the way until we're at the last level. The, and if we remove the last set of nodes, the tree will become empty. And that last set of elements will be our solution. And and from the algorithm that I just discussed is going to be a ON time complexity because at each step I'm reducing the number of nodes that we need to look at, and each node will only be looked at exactly once. So yeah, and space-wise, we're basically duplicating the edges, duplicating uh, the graph here to a easier to understand format. So we're making a copy of it. So I will call that ON as well. So here we go. So first, no matter what, we need to build an output as a result. And one edge case, if there's no edges for a particular node at all, and we can just there will be a zero node, and we can just return the result. This is error case checking, and then we can start building the graph to something that we're familiar with. I'm going to use a map where the key is the nodes, and the values is all of its child/parent nodes. And I can use a set just for easy lookup and deletion. And let's call it a graph. And now I can start populating it. First, I need to initialize it. So I will iterate through all the parent-child pair type edges and make sure that initialize them. I'll do the same for the second element, and then I can start populating for real. What I can do here is, so each pair, 3 is child 1, and 1 is also a child of 3, so it's communicative. So I can first get a particular element child hash set, and I can add the other element as its child, and vice versa. All right, so at this step, we have populated the map. And another thing I want to do is to keep track of the um, amount of childs or parents a particular node has. If it only has one child or parent, that means it is a leaf node, and that means we can remove it safely without any changes, without destructing the structure of the graph. So I'm going to sense every node is in order, and there's at most n of them. So I'm going to use a degree array to keep track of the amount of incoming edges for a particular node. And the node is represented as index at each index. So I'll do that, and I'll calculate the degree of each element by 1, increase it by 1, because it's have a incoming and outgoing edges both need to be initialized. And then I can iterate through the degree array, and all the degree with all the nodes with a degree of 1 are the elements that we can process on the first iteration. So let's do that. So if it's 1, we know that that's something we can process. And to process, we need a queue that so for a queue, all the elements inside the queue will be the elements on the current iteration that has only one edge, and on each iteration we'll append to the queue any additional node that becomes a node that only have one incoming edge. So the queue, I'll use a deck data structure in Gala. So I will need to append this to the queue with its index. And then we can start doing the trimming of the graph. So first we need a size. This ensures that we only remove size numbers of elements from the queue. So all elements that we move at the current level is this element has only one edge. And in other words, they're on the same level. And yeah. So here we know the parent node is actually the child node is equal to the element inside the queue, and we want to iterate through all the elements that this child connected to, because we're removing it. So all the all the nodes that this child is connected to we need to update this in degree count, decrease it by 1. And if this degree becomes 1, meaning this element becomes another leaf, the new leaf node, we need to populate that into the queue. So for each parent this child has, which is we're going to do by getting the parents by calling the graph, give it a child, and now all the parent nodes are visible to us. So we need to decrease the parent node's degree by 1, and if degree parent becomes 1, that means we have look at we've saw a valid node that can be removed. So I need to add the parent into the queue. And yeah. So, and another thing that we need to do is we need to keep track of the elements that we are currently removing. So because that round of removing might be our solution, because the last time we remove, the last iteration will be all the degrees. The graph.get here will give us all the childs will only have one edge connected to something else, and we want to record them so that can be our solution. So what I'm going to do is duplicate a output array. So we call it temporary. And every time we move, we know that this might be a potential solution for our question. So we can just add the child into our list. And after iteration, we need to keep a copy of it so we can just assign it to our result. And last but not least, we can just return the result. All right, let's see. Edge.length is equal to line 4 edges. Result. Line 18 pair 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 PAIR. Let's see. All right, that looks good. Let's submit. All right, so yeah, like I said, the time complexity is just iterating through we're building a copy of the graph, which is of n, assuming that n is number of nodes. Actually, it's number of edges plus number of vertices. And we're doing this twice because first time we're populating the graph, and the second time we are iterating through it. So, but that still gives us all of the edges plus number of vertices. And space-wise, we're using a queue, which is at most number of nodes. And we are also making a copy of the graph, so that will be all of number of vertices plus all of E plus E. Okay, thank you.